In this lecture, I want to talk a little bit more about the effect of ligands and metal oxidation state on the size of that crystal field splitting energy. And it's important to remember that we're really balancing two things here. We're balancing the effect of the ligands and the effect of the cation on what that energy actually looks like. So we can't usually directly compare between two different metal ions. When the cation itself is different, we kind of need to have one of our variables be the same. Either it's the same ligand with different anion or cations, or the same cation with different ligands. So the general trends we see when we explore that are that for the way the ligand affects the crystal field splitting energy is that the larger gap will be created by strong field ligands. And so those are going to be things like cyanide, nitrate, ethylene, diamine, and ammonium. And they're these ones right here. Um, and then we'll see smaller energy levels for splitting from our weak field ligands, which are going to be our water through our iodine. So there'll be these ones right here. And these are relative field strengths. So iodine will be a much weaker field ligand than something like water. And so we don't have a very clear cut, in my opinion. It's not black and white. Well, water always produces this specific amount of change. And so it really depends. But this is kind of a trend that we see that we can make predictions based off of, but we would need to confirm experimentally any conclusions we would draw from it. So that'll be the effect of the ligand, and you just have to be comfortable referencing this series of ligands here. And then the other effect on that splitting energy is going to be the cation, and we'll see a larger crystal field splitting, so a larger gap, when there's a larger charge on the metal. And so as that charge goes up, we see a larger crystal field splitting energy. And so something like cobalt is going to have a much larger gap in it or a much larger crystal field splitting than an ion that doesn't have a +3 charge, but is a +2 or even a +1. And again, this isn't a black and white. There isn't a clear delineation between this one will always be like weak versus strong. But rather it's a consideration to take into account when evaluating these energy differences between our d orbitals. And so let's talk a little bit more about at least the ligand effect. And so here is a series of different compounds making up pretty close to a rainbow. We're going from a nice dark orange red to orange to yellow to green to a dark blue. And these are all copper ions. Like every single one is a copper +2 ion. And the difference between them is the ligand that is coordinated to that copper +2, and that's it. And so this is something where we've held that metal cation variable constant and have changed our ligand across the series. And so my question to you is, which end of this spectrum of color corresponds to weak or strong field ligands coordinated to the copper? Does that blue color correspond to a strong or weak field ligand? And does that reddish color correspond to a strong or weak field ligand? Take a pause, think about it. Take a minute to think about it and see if you can just like come up with it, talk yourself through it, and then I'll talk through it. But first try it on your own. Okay, assuming you paused and have now restarted. Let's walk through what we know about these. Let's just divide this up into seeing red and seeing blue. So when we're seeing red, right, we're not actually absorbing red. So if we go to our color wheel that we have, if we see red, then we're absorbing blue-green, which is really going to correspond to wavelengths anywhere between 430 and 560. And that's a broad range I grabbed there because I'm not sure exactly which wavelength this one is at. So that's what that red color means. And if we are seeing blue instead, then that we're really absorbing in the red and orange region, which is going to correspond to wavelengths that are more like 580 to like 750. Again, broad range, but you get the idea. This is a broad enough range, it's fine because we're just looking at a comparison of like, what is the difference between these wavelengths, right? And so we can see that we have a larger wavelength for when we see blue, and we're absorbing a smaller wavelength when we are seeing red. And so now it's important to remember that equation we've been using, that energy of the photon or energy of that crystal field splitting is equal to Planck's constant, speed of light, over the wavelength. And what I draw from this is that that energy of the crystal field splitting is proportional to the inverse of the wavelength. So they have an opposite relationship. So the larger that wavelength, the greater, so as this number gets bigger, as this number gets bigger here, my energy here gets smaller. Or as my energy gets bigger, I'm going to expect a smaller wavelength. And so that means when I see small wavelength for when I'm seeing red, I know I have a high energy. And when I'm seeing a larger wavelength, I have a smaller energy for my crystal field splitting. And so that's now going to help me move on to which is weak and strong. I know my weak field ligands are going to produce a smaller difference in energy. And so that means I'm going to have a weak field ligand over here when I see blue. And I know my strong field ligands create a larger split in my energy levels. And so I'm going to have strong field ligands when I see red. And so my spectrum of different ligands that are strong versus weak are going to have my weak ones down here by blue and my strong ones by red. So if I was going to go out on a limb, I would say that we might have something like cyanide ions here and iodine at ions in my blue.